All right, Ejner. So listen, I've made a few videos of the TU valve discussing it, how it's stainless steel. I've one of your colleagues here in Canada who lives very, very close to me, Jamie Kitchen. He's come over to the back of my van. We have discussed it. We have brazed one end, and he was actually holding the TU valve in one of the videos while I brazed the one side in. And the reason being is because the stainless steel does not transfer heat nearly as fast as copper would, let's say, right? And
Okay.
that's why he was allowed to do that. And part of your instructions for the TU valve is you don't need to wrap it. And when I tell people that, they say they're going to wrap it anyway. Give me your thoughts on that, please.
Yeah, my thoughts is because you're absolutely right. You don't need to wrap it because the heat conductivity of stainless steel versus a copper connector is 1 to 20. So you have 20 times less heat going into the product itself. Now, this is not pure stainless steel because it's a bimetal connection. You have a copper on the inside, a cladding of between a copper sheet, thin 40 micron, and some stainless steel on the outside. So there the ratio is 1 to 11. So 11 times less heat will be transported into the valve itself when you do your brazing. And therefore, you don't need to wet rack it. And if you wet rack, you actually have a risk of having moisture close to maybe even getting into the product itself. Plus, the cloth you're using for making wet and wrapping around, over time, you have the flux and so on that will get into it. And now you have acid on the product. Now you don't need to because you don't have any of that on your product itself.
Mm-hmm.
And you're absolutely right. You could hold it, and you can do all three connections here. And I'm not an expert in brazing, but I think I could do it in something like 30 seconds or 25 seconds. I could have all three done. Where a traditional product, being with the copper connectors, brass housing, which is also heat conductive, there you would use something like 4.5 minutes to do it. So
Mm-hmm.
it's super fast. And I like to call it waterless brazing because you don't have any waters around because
Yeah.
you don't need it.
One thing I want to add to that is I didn't use like a silver solder that needed a paste or anything when I brazed the one in for the demo. I used 15% silfos, and because it's that copper on the internal part of the connection, you can use silfos no problem. So you don't have to introduce flux into the system. But one of the thoughts I'm having is if you do wrap it, right? Let me go back for a minute. So for a TX valve, any heat sensitive valve, you want to get the heat on and the heat off as quick as possible, right?
Right.
So if you do wrap it, what that's going to actually cause you to do is keep that torch on there longer because that rag is keeping the valve cooler. So you're actually keeping your torch on there a lot longer. If you pull
Right.
the wet rag off, your torch is on there very, very shortly because you heat up the valve quick or you heat up the connection quick and then you get it off quick. And that's my mindset behind that is putting a wet rag around it could actually be a negative when it comes to the heat, right? How fast that or how long you've got that heat on there for. What do you think of that idea?
Exactly, but even if you have the stainless steel, the heat will not even get to the wet rack because the heat is kind of being blocked by the stainless steel, so
Mm-hmm.
it stays at the connector itself. So it's kind of wasted to even spend time on wet racking it.
Gotcha. Okay.
And you have that additional risk of having water around the connection and maybe even get it into the system. And then the filter dryer has to do clean up afterwards. And you eliminate all of that. And
Yeah.
you have to a little bit get used to it and trust that you don't need it because it's almost like it's a stainless steel to copper. And that can be difficult, but it is not. It's copper to copper because you have a copper clad on the inside of the connector itself. So you have to treat
Yes.
it as use the same brazing material. But guess what? You don't have to wet rack it, and you can do much faster and get to the real issues that you might be on site for.
Yeah. Okay. All right. So we've got that covered. So maybe take us through the operation. Maybe like spend 2-3 minutes going through the general operation of a TX valve, and then we'll talk about how this one gets adjusted. And you have like isn't it at the bottom? If you hold it up a little higher, the bottom there, you can pull that out, right? There's a cartridge in there. Oh, the cartridge is
No,
in there.
this one has a fixed orifice, but you can
Oh,
get
that
some
one's got a
versions
fixed
that has
orifice.
also
Okay.
with a cartridge where you can adjust or you can select the right orifice for the right system conditions.
Gotcha.
And therefore we have 9 different orifice sizes. So, but this one there just happens to be one with a fixed orifice.
That's a fixed one. Okay, perfect. So take us through the operation of the TX valve for a couple minutes, and we'll talk about how you adjust that one.
Yeah, the operation of an expansion valve, the whole purpose of a thermostatic expansion valve is to control superheat. And superheat is the difference between your gas temperature when it leaves the evaporator and the saturated pressure or temperature of that evaporator. The difference of those two, that is the superheat. So that's what it's trying to control. So if the gas coming out of the evaporator is higher than the set point, it will inject more liquid into the inlet of the evaporator in order to lower down or fill up the evaporator better and then lower your superheat. The same the other way around. If you take load off your evaporator, of course, less boiling will take place. Your superheat is going to go down. And now the valve is going to see it because it looks at it with the sensor bulb itself and the pressure on the equalizer port. And then it will start closing down the valve to exactly match the load that is on the evaporator itself. So that's the whole purpose of a thermostatic expansion on.
Now, the bulb, does this one have an equalization line that
Yes,
an
the equalizer is sitting on the side. So if you look here, we have inlet and we have outlet. And then this has a third connector, and that is the equalization line. That pressure goes under the diaphragm, and the bulb is actually pushing on top of the diaphragm through the cap tube itself.
Correct. So we have three pressures or three forces on a TX valve. Do you want to talk about those real quick?
Yeah, you have from the top, you have the bulb. So if I heat this up here, I'm going to heat up the gas on the inside. It's going to increase the pressure and push down on the diaphragm, trying to open up the valve. Then I have two from the bottom. I have the equalization, which is the pressure in the evaporator. So that's the evaporating pressure, the same that you would see on your manometer. And then I have a third one, and that is my adjustment screw, because there's a small spring sitting on the inside. You can't see it here. That also helps push to close the valve. If you increase the pressure, it will close. So when I want to alter my superheat setting, I basically just adjust the compression of that spring that is sitting in there. And that will increase or decrease the superheat. So those are the three forces that are working in it.
Perfect. Now, Danfoss has some nice, I don't know if it's an animation, but I think it's more of like a diagram of how to install the bulb. Like there's a proper way to install the bulb on the suction line, like up, down, sideways. Do you want to talk about that for a sec, if you don't mind?
Yeah. As you go up in size on pipes, you have to be careful to have laminar flow. And therefore, you don't want to put it like at the bottom of your suction pipe. So put it below your suction pipe. If you have an oil running down there, then it can easily misread. So you want to put it at 5 o'clock or 8 o'clock, something like that. You don't want to put it in the top of the line of a horizontal line either, because it might not be picking up all the correct gas temperature, because what it has to do is to just sense the temperature in that suction line, right? And you don't want to have misreadings from things. You also don't want to put it on the riser. If you have a riser, let's say you're in a walk-in cooler and you're coming out through the ceiling in the walk-in cooler, and you have a riser there, you don't want to put a bulb on the riser, because it will pick up oil and you will have these small slucking coming. It doesn't harm anything, but you have these small slucking which picks it up. And you don't want to have that on there, because then all of a sudden it sees a sluck and it'll drop in temperature and give kind of a misreading. So you either put it before you have your riser or right after where you have your riser.
Perfect. Okay. Awesome. Now, the adjustment on this. Now, so there's a bunch of valves out there where you adjust from the bottom. This one's a little bit different, right?
But it does exactly the same. It depends a little bit on configuration, can be slightly different on how they work in an expansion valve. Some or many has the adjustment at the from the bottom on. That's typically balanced ported valve that would have that. But this one here has it on the side, but it's doing the same. It's compressing a spring under the diaphragm, and that is adjusting the superheat itself. So it works the same way. It's just, how do you now adjust superheat? You know, what should you do in different situations?
So you have an Allen key in front of you. Is that the only?
I have an Allen key on this particular here, the TU valve from Danfoss. There's a small cap here. The Allen key will fit in there, so you can actually remove the cap. On some other valves, it's a big brass. You get your fixed key and you adjust it. Inside here, you also have an Allen key, so the same one actually fits in here. So now it's sitting on there. Now I can start adjusting the valve by going counterclockwise or clockwise around the valve. And if I go clockwise, I compress the spring more. Compressing the spring means I increase the superheat setting. If I go counterclockwise, I decompress the spring on the inside. And I can actually feel it, because I can feel the force here. If I go this way, clockwise, it gets stronger. And if I go counterclockwise, it actually goes a little bit easier.
Yeah.
So counterclockwise, I decrease the superheat. Clockwise, I increase the superheat.
Yeah, I always, in trade school, when I was going through my apprenticeship and I went to trade school, one of the ways I remember which way to turn the stem in order to increase or decrease superheat was increase spring tension, increase superheat, decrease spring tension, decrease superheat. That was
absolutely
one of the ways I remembered that, right? So
absolutely correct.
Very good stuff. Is there anything else that we can? I mean, I think we've covered a lot of this, like installation, how it works, how to adjust it. Is there anything else that you find important
That
about this
would be
particular valve?
optimizing, because how do you now optimize your system? We, as all our competitors and everyone, we deliver valves with a preset factory setting, we call it. And it comes at a certain setting, and that's always, we have to be at a safety point. We don't know what unit this goes into. We don't know whether that's it's a walk-in cooler up north or down south, or what is in it. Is it a freezer? Is it a cooler? So we have to be safe, on safe ground all the time when we factory setting. So we set it on the high side. Anyone does that. That doesn't mean it's super optimal to that unit that it goes into. It might, by lucky draw, be optimal setting. But if you were to optimize something, you have to know what you do. And one thing is that what you want to have in a system to actually increase your COP or coefficient of performance, that is to lower the difference between your air temperature and your evaporating temperature. Because if that's too high, your cooler is actually colder than it needs to be. And if it's too high or too low a difference between the two, you might actually be starting to flood your evaporator, and that has other consequences. Mm-hmm. So the most optimal COP is what we call the minimum stable superheat. That is, lower it as much as you can. Don't go too low, and don't increase it too high when you do that.
Okay, so I mean, I guess it depends on the application too, because there's you have to pull out your manual for that specific piece of equipment, because sort of there's always a rule of thumb, but there's always specifications that one manufacturer might want over another, right? So it's always best to just get in touch with them or pick up a manual and see what they recommend for your superheat setting. And the superheat could be right at the evaporator. Some of them want it right at the evaporator. Some want to check it right at the compressor too, just to make sure.
Exactly. And there's different ways of doing, because, the way to check it is, of course, get your manometer on there and get your temperature probe on there, and then look whether it's oscillating or you have a stable superheat. If you have a stable superheat, then there's a good chance you can lower it even further. So you give it a little tweak, and now you monitor again and see whether is it still stable, the superheat, and it's especially the bulk temperature. And if it's stable, you try to lower a little bit more. Try to lower a little until you get instability, and then back off a little bit. Then you might want to change that, check it, that it also works at other conditions. Let's say you were doing with an empty cold room when you did the setting. But as soon as you load it with goods, just check again that it's okay, Yeah. But the point is that if you optimize your superheat to an optimal point, you might easily gain 7, 10, 11% of better COP. So less running cost, less electricity goes into your compressor if you optimize your superheat. 9 out of 10 expansion valves out there, they're never being optimized, right? So there's a lot of untouched.
If it's optimized properly, essentially you're going to get more net refrigeration effect, really, right?
Exactly. Yeah. Exactly. Okay. You get more refrigeration. You have less run hours. If it's a cooler, you need less defrosting. If it's a freezer, because you are running your evaporating temperature at a higher level. So there's a lot of positiveness to it. You also have less dehydration going on, and that results in a need for defrost. So if you add fruits or something that is, you can keep it longer, and you're not pulling moisture out of the product itself. So it has a lot of positive consequence besides less running cost.
So the EEV, Ejner, you had that holding it up if you want for us there. Now talk about how that's a little bit different from the mechanical valve.
The EEV, or the electric expansion valves, that's a motorized valve, and it's actually a little bit a dumb valve because it can't do anything on its own. It needs a controller and it needs some sensors to it. And then all of a sudden it can do the same as a mechanical thermostatic expansion valve can do. But what the advantage you have with the electric expansion valve is that now you can put some algorithms in that actually can do the automated optimization of a system. We can make it go search for that optimal superheat setting. So it'll try to constantly lower until it gets a little bit unstable. Then it will back off again. And then 15 minutes later, it will try the same once again. And that's what we call adaptive superheat control algorithm, right?
Yeah.
Some of the other things a electronic expansion valve has, that is also that it can have a wider operating range. With a mechanical valve, you can only go so much on the operating range, with a cap tube even less. But with the electric expansion valves, you can have a wider operating range. So you can go full steam, and you can also go really into part load if there's need for it, if you have a holding temperature you want to hold in a cold room or whatever it is, right? So those are the main differences.
Those valves there, don't they have like a few, like in the positions they can sit in? Isn't it over 100 or a couple of hundred positions that can actually sit in?
Yeah, like this one here has actually, I think it's close to 600 steps. So you have increments of 600 different steps you can put it in.
Yeah, so having
And some, if you go by
six
the bigger ones, they might have over 3,000 steps.
Yeah. So I mean, if you have a valve that has 600 different steps or positions to go in, that's some real fine tuning right there, right?
Yes, exactly. But the real fine tuning happens if you look at the system conditions. How optimal am I running? So it keeps an eye on the superheat by having a temperature and pressure sensors on the system. And then it constantly tries to see, can I actually lower this one? The same as a service technician would be doing with a mechanical valve, where they would be looking and have the gauge and temperature probe on the suction line, try to adjust the superheat sensor, but we cannot have a technician sitting here 24/7 all year round. With the electronic, we can easily do it because the electronic has nothing to do but just optimize. So it
So
constantly tries to adjust and fine tune the superheat setting.
yeah, so I when you bring it up and you say you can't have a technician sitting there adjusting it 24/7, it was a pharmaceutical building, right, that I was at. This is like 3 or 4 years ago, where this job was the thermal expansion valve, it was not feeding properly. It was not getting the right superheat, and the unit wasn't running that great. In order to get to the valve, you had to drive around to the back of the building, right? And in order to get to the back of the building, you had to go on another street, drive
Exactly.
around. So,
Yeah.
and I was by myself. So I go in and I'm adjusting it slightly, and then I got to go out. I got to
All the way around
drive
again.
back around the building and go up the
Exactly.
ladder and then walk forever across the building because this was a big warehouse, and then check it. Is it? But
See what impact it had.
that gave me the 15 minutes of stabilization. So I was like, okay. And this literally took all day to dial in the superheat because I was
Exactly.
by myself. So
Exactly.
it happened on the second one where it was kind of off. And I'm not sure if going forward the valves were changed because I left the company. But on the second one, I'm like, I've been here before. I said the dispatch, I said, you're going to send me another guy. You're going to send me another guy. He's going to go into the freezer. He's going to adjust it, and I'm going to sit up on the roof and I'm going to watch everything. And that worked out
Exactly.
way better, right? And that's sometimes in these large commercial applications, sometimes you need two technicians on site just to get through a simple task like that.
Exactly. And sometimes you might even have to move products in the cooler itself or the freezer itself, even to
Yeah.
get to the evaporator, right? And that's where the electronic, because you can sit remote. I could even do it from my desk.
Yeah, and once you have the correct sensors
Yes, it's all
inputting
connected.
into some sort of controller, then the controller says, hey, stepper valve, step up, step down, and it
Exactly.
continuously keeps moving. It doesn't just stay in one
Ex-
position; it just
oh,
continually tries to
absolutely.
optimize the system, and that's what's cool about the
Yeah,
EEVs,
yeah.
right?
Absolutely. Absolutely. Of course, it comes at a cost because it's not only about the valve. It's not only comparing the mechanical valve to the electric valve because you also need the controllers and the sensors. But if you have systems where you have controllers on board already anyway, so you have already paid the base price. So it's going to an EV, so it might not be that much more expensive. And
Now
you get the COP optimization all by itself.
yeah. So what about installation? Is there installation any different? I mean,
Oh,
it shouldn't be, but I think something that's really important is if you're gonna braze, you need to flow some nitrogen just so you're not
exactly. Exactly. And
creating that copper oxide that because those EEVs because they're such small increments, you could block one of those up with that copper oxide, no problem.
yeah, but you can actually do the same for the mechanical valve. You have to
Yeah.
always, when you do installation, you have to use protection gas to prevent the scaling of oxidations on the inside. You always want to make sure, like if I'm bracing this one here, then the flow of nitrogen has to go in here and then away from the valve
Yeah.
because there will be heat on the inside, and just having a small amount of nitrogen flowing, first of all, it will protect from scaling, but it will also take the heat away from any sensitive part you might have the inside, whether it's electric expansion valve or mechanical valve. And
Yeah.
then when I do the bracing on the other side here, I reverse my flow of nitrogen so that I in here and then out, so that any heat that is on the inside gets actually dispersed away from the product itself.
Yeah.
And
A
that's what
very
you have
good
to remember.
That's a very good point. The nitrogen flowing actually removes a little bit of that heat as you're brazing, and that's something
Actually,
that
quite a bit.
yeah, it's actually something that a lot of people don't even talk about or discuss
Exactly.
on top of
Exactly, exactly. And like if you take mechanical valve, I can't see it here, but there's actually a teeny tiny small filter or strainer on the inlet here. And if you have scaling, you don't have protection gas, that's going to clog up pretty fast. And now the
Mhm.
first thing you have to do is probably do service on your system.
Yeah. Yeah.
But it's no different whether it's EVs or it's mechanical valves, brazing and all that is the same. The TU we just saw, that's a bimetal connection, so that has its absolutely advantage over the over pure copper, right? But like this one here has stainless steel housing, so again, it's super protective from heat. So it has a very good heat barrier when you are applying the brazing flame to it.
Perfect. So Ejner, I mean, this has been a great conversation. I love when we do these videos and the guest actually has a piece of equipment or a part in front of them and they can do a bit of a show and tell. So this was very cool.
Excellent. And I'm
for the
sure
audience, for the audience listening, I will be posting some of these little small videos on social media, and I'll probably get the whole thing onto YouTube as well, so you guys can get a visual rather than just listening. Because I know it's hard when you're driving along in your van and you're trying to understand what you're talking about without seeing it. I get that, so we'll try to get this on YouTube as well, so everybody can watch it.
it's a
All right. Yeah, thank you. All right. Well, you have
interesting
yourself
topics.
a great weekend, and
Same to
we'll
you.
do this again. We'll do this again.
Absolutely. And if you ever need some topics and all that, just let me know and we can do something.
Thank you very much. Oh,
right?
Ejner, hold on. I'm going to stop this.